Well, good morning. Before I turn over the mic to John Goldbeck to introduce this morning's speaker, let me make just a few quick announcements. This is supposedly a room without food and drink. So please clean up after yourself and take the trash out. There are recycling bins all over. That would be great. The other thing is that if you have problems installing Orca, are there people who have still problems installing Orca? Showing of hands? 2, 3, 4, 5. Okay. In the Orca room at the coffee break or the lunch break. I think the lunch break. Okay, lunch break at the Orca room. Okay, that is room 301A. Okay? I think that's it. So let me turn over the mic to John.
Okay, thank you, Karsten. I'd like to welcome everybody to this morning's session on introductory EPR spectroscopy. My name is John Goldbeck. I'm a professor in the Department of Biochemistry and also in the Department of Chemistry. Our lecturer today is going to be Art van der Est from Brock University in St. Catharines, Ontario. Art is a member of the chemistry department and also the physics department at Brock University. And he's a longtime EPR spectroscopist. In fact, he started his career at the University of British Columbia and then spent probably more than a dozen years in Berlin in the physics department, and then took a position at Brock University probably about 12 or 13 years ago. So Art has also written a number of chapters on introductory EPR. So if they're not in the folder, just Google his name, and you'll find some of these chapters. They're really good. In fact, I brush up my knowledge of EPR by reading them periodically myself. So without any further ado, we look forward to your talk, Art, and we welcome you to Penn State.
All right, thanks, John. Thank you. So first of all, can you hear me okay? Is that everything good? Okay. All right, so it's a real pleasure to be here again. I always enjoy coming to these workshops. I learn a lot, and it's nice to help out with the teaching and so on. So what we're going to do this morning is, of course, talk about EPR. My goal here is to give you guys hopefully a little bit of introductory understanding of how the technique actually works and why EPR spectra look the way they do in general. So I've seen over the years that many people, many chemists use EPR but have a somewhat vague understanding of why the data that they're looking at actually look the way they do. So if I can help in some way to clear some of that up, then we'll have achieved our goal here. Okay, so EPR spectroscopy, of course, is magnetic resonance on unpaired electrons. Right? So we can only study substances that have unpaired electrons. And so if we look at the types of species that we can study with the method, of course, free radicals is an obvious species where we have single unpaired electrons. But of course, transition metals, which have odd numbers of electrons, or if they're in a high spin configuration, will be paramagnetic, and so we can study them with the method. And then an area which I work in a fair bit, which is a little bit neglected maybe, is that we can also look at excited states which have a spin not equal to 0, right? So if I excite a molecule into its triplet state, we can observe this. And we have a practical, the EPR3, where we look at some triplet states. What's actually very important for EPR, which is sometimes a little bit not mentioned so much, is that molecules that have paired electrons, of course, have no magnetic moment and therefore have no EPR spectrum. And that turns out to be sort of a two-edged sword. It's a bad thing because, of course, there are many compounds that you can't observe with this method. But on the other hand, it can also be a strength because if there are compounds present in your sample that you don't necessarily want to see, then, of course, they don't interfere with your spectrum. Right? And so this is a bioinorganic meeting here. So this is I just want to mention a few things about how it's used in bioinorganic chemistry. Right? So in bioinorganic chemistry, of course, we're looking primarily at metalloproteins and their function and all these sorts of things. And most metalloproteins are involved in redox chemistry. Not all, but this is one of the main functions of them. And the active sites of the proteins, of course, are the metals, usually. And so if you have a transition metal and it's doing redox chemistry, more often than not, one of the states or some of the states of the metal will be paramagnetic, right? So you have either odd numbers of electrons or high spin and so on. And so there are really two general classes that we'll cover here. There are metals where the spin is a half, and then there are situations where the spin's greater than a half, right? And it turns out their EPR spectra are really quite different. Anyway, these states can be studied by EPR, and what's important here is, as I said, because we don't detect in EPR molecules that have all their electrons paired, if I have a large protein, I don't see anything from the protein, and all that I will detect is the metal, right? But of course, that's where all the action is in a metalloprotein. So we get to see the active site without any big background signal from the rest of the system, right? Anyway, so there's a whole long list here of different types of proteins that we can study. So iron-sulfur proteins, heme and non-heme iron proteins, iron-nickel, copper, and so on. So a wide range of metalloproteins that can be studied by EPR. Okay, so this is sort of our plan of attack here. I'm going to start by talking a little bit about how the experiment is actually performed, because unlike many other forms of spectroscopy, there are quite a few differences in the way we have to detect the signal and the way it's presented when you look at a spectrum and so on. And so I'm going to touch on some of these experimental aspects to show why EPR spectra look the way they do. And then we'll start looking at EPR in proteins at low temperature and look initially at systems with spin 1/2, right? Because these are a little bit simpler. And we'll talk a little bit about G anisotropy and some what information we can get if we look at single crystals and powders, which are more common, or what we call powders, and talk a little bit about hyperfine interaction, so the interaction between the electrons that we're observing and the surrounding nuclear spins. And then at the end, we'll talk briefly about high spin systems, so where we have the overall spin greater than a half. And here, the zero field splitting plays an important role. So we'll talk a little bit about what that is and how we can analyze these sorts of spectra. Right? So what, or at least what determines their shape. All right. So just John mentioned some chapters. So here are some references, some places where you can find information which is maybe goes beyond what we can do here today. There's this book by Hagen, which came out in 2009, called Biomolecular EPR Spectroscopy. And this is a great book for someone who's not an expert and doesn't have a really strong background in physics and so on. It starts at a very, very qualitative level and talks about really practical things like how do I prepare my sample and how do I put it in the spectrometer and tune the thing and so on. But it progresses, and in the second half of the book, there is lots of theory and so on if you want to learn more details. So this is a really good book. There are a couple of others here. This is also has lots of practical information. This is a book with contributed chapters from a few years ago. Weil and Bolton is sort of a standard text on EPR. It's fairly heavy on the physical chemistry, but if you're interested in that kind of thing, it has lots of good stuff in it. And this is a chapter that John and I wrote a couple of years ago. Okay, so EPR, of course, we're measuring the paramagnetism in a system. And so if we look at an electron, of course, it has spin angular momentum. Right? And so what we have is a charge, and it has some kind of angular motion in a sort of hand-waving way. We can represent that as a sphere with some kind of spinning motion. The upshot is that there is this angular momentum. We're moving the charges in a circular way. And the angular momentum here is represented by this vector. And of course, if you take charges and move them in some kind of circular path, then you create a magnetic field, right? And so there's a magnetic moment associated with the angular momentum, and it just points in the opposite direction. The proportionality between these two you can write this way. So there's this factor G, which is a fundamental constant, is roughly 2. You can see down here there's a small correction to it, which comes from relativistic effects, but basically the number is 2 here. This is the Bohr magneton, which comes out of the Bohr model of the atom, just working out what the magnetic moment for a circulating electron should be. And then we have the spin quantum number here, right? And this is basically the length of the spin vector here. And so for an unpaired electron, we can work out very easily what the magnetic moment is. Then if we put our spinning electron into a magnetic field, we have an interaction between the magnetic moment of the electron and the field. And because the magnetic moment is quantized, it's a quantum mechanical property, we get a pair of states, right? And so if the electron or the magnetic moment is aligned with its z component along the field, we have the state with ms plus 1/2 and the state of minus 1/2, and there's an energy splitting which is proportional to the strength of the magnetic field, right? And so if we have radiation that matches this energy gap, then we can do transitions between these states, right? And this is what we observe in an EPR experiment. All right, so most people have maybe a better understanding of NMR, so it's useful to do a little comparison with NMR. It's basically the same technique, same principle, but there are some really profound differences actually in the way nuclear spins behave and electron spins. So the first thing is that an electron is much, much lighter than the nucleus of an atom, and so its angular momentum is much larger. And so the resonance frequencies that we work with are roughly about 600 times bigger than what you would have for, say, protons, right? So if I take a 300 megahertz proton NMR spectrometer and use the same magnet to do EPR, then I would be working at 180 gigahertz, right? And you can convert that to wave numbers, so 180 gigahertz is 6 wave numbers. So we're in the far infrared region or in the microwave region of the electromagnetic spectrum, right? So the first challenge that we have in doing EPR is that we have to work at much higher frequency than we would doing NMR. And then the other thing is that the couplings, so the interactions between electrons, are much stronger than in NMR. In NMR, the nuclei are well separated. They don't move around, so they don't interact nearly as strongly as electrons, which are delocalized and can approach each other much more closely or come in much closer contact with the nuclei and so on. And so this leads to really, really broad spectra in EPR, right? So in NMR, typical spectral width is somewhere between 1 hertz would be a really narrow NMR spectrum, and 100 kilohertz is a very broad solid-state spectrum. And if you compare that in EPR, the widths are, from a megahertz is a really narrow one, and you can EPR spectra can be as broad as several gigahertz. Right? So we're, thousands of times wider than an NMR spectrum, and this also has really important consequences for how we do the experiment. The other really important factor, which is different from nuclear magnetic resonance, is that electrons have 2 types of motion that they can undergo. They have angular momentum associated with the spin, but electrons also are located in orbitals, and they have orbital angular momentum. And both of these motions create a magnetic moment, right? So I have a spin magnetic moment and an orbital related magnetic moment. And these two have slightly different forms. They look very similar, but this factor G is equal to 1 for the orbital angular momentum. Right? So if I'm measuring an electron, what I will measure is the interaction of the total magnetic moment, which has these 2 components associated with it. So what I have then is that the total magnetic moment is related to the total angular momentum, which depends on how the spin and the orbital angular momentum add together. Right? And so my total magnetic moment is a factor G now. This is not the free electron G value, but a G value for the individual case depending on how the orbital and spin angular momentum add together, and then is related to the quantum number for the total angular momentum. So if we're looking at a molecule, the orbital angular momentum if an electron in a molecular orbital usually does not have orbital angular momentum, or at least it's quenched, right? And so this means that our J here is approximately equal to S, and our G is approximately equal to the free electron value. So this factor which determines where we would observe our resonances, this G value, it's approximately equal to 2. But the exact G value depends on how strong the spin-orbit coupling is and how much residual orbital angular momentum is present, right? So if I look at, for example, copper-2 just in a copper salt, we might get a G value of 2.1, right? Or titanium-3 and titanium oxide is 1.9, right? So there are slight shifts away from this value of 2 because of the contribution from the orbital angular momentum. But that contribution is normally relatively small. And so, of course, we can use then these values. If we can determine that from a spectrum, you can use that to identify which species you're looking at. Okay, so then an important question, of course, is also how do we decide what magnetic field to use and which frequency? And that's determined largely by the availability of microwave components, right? And so microwave components are produced at generally at fixed frequencies that are used for other purposes, so radar technology, cell phones, this kind of thing. And so EPR, of course, is a relatively small market for microwave components, and so we're kind of stuck with the frequencies which are, where the components are mass-produced, right? So one thing that's a bit odd about EPR, so these are the frequencies that are typically used. There's a range of them. And one of the things that's a bit unusual about this is that each of these frequencies has an associated letter. And these letters have absolutely no meaning. They were originally developed actually in the Second World War and were a code that was intended to make it hard to tell which frequency was being used in radar, right? So there's no pattern at all to these letters, and you simply have to know what they are. But we still use them today routinely. Rather than saying what the frequency of the instrument is, we use this letter, right? And we refer to a frequency band. So there's L band and S band and X band and so on. So if you have a EPR spectrometer that you have access to in your department or so, chances are it's an X-band spectrometer. Almost all EPR spectrometers operate at about 9 gigahertz and at a field of about 0.3 Tesla or 3,400 Gauss. Q-band spectrometers are also fairly widely spread. W-band, which is known as a high field instrument, there are a few of those out there. They're commercially available and becoming maybe a little bit more common, but they are not really that easily available. And low frequencies are often also not that commonly used. So what we're going to talk about today is primarily X-band spectroscopy. All right, so if we want to do a spectroscopic experiment, the way that we do this usually is we take our sample and we put it in some kind of a holder, right? If I'm going to do a UV visible spectrum or IR spectrum or something, I put my sample in some kind of cuvette. I have a source. I shine my light or electromagnetic radiation through it, and I measure how much of that is absorbed by the sample, right? And then I can work out the absorbance as the log of the ratio of the initial and final intensity, right? We can't do things easily this way if we're going to do EPR, right? The problem here is that the absorbance is very, very weak, right? And so we run into technical problems trying to measure the absorbance in this way, right? There are a few exotic, very high magnetic field instruments where the absorbance is measured, but in general in EPR we can't do the experiment in this way. So, and the problem really is the question of sensitivity. So the absorption is very small, And so it's really, really difficult to see the small changes this way. And we have to resort to other methods to improve that. So one of the things that we do is that we use a resonator. And this, sort of in a very rough analogy, kind of acts a bit like the sound box on a musical instrument, right? So if I have a guitar and I don't have the sound box at the back and I pluck the string, the sound is really small. If I put the resonator at the back of that, then it amplifies the resonance. And the cavity in a resonator in an EPR spectrometer kind of achieves the same thing. So the idea is that we bring our microwaves into some kind of enclosed cavity, usually made out of metal. Very often it's some kind of rectangular shape, but there are lots of different designs, and they have their advantages and disadvantages. But inside this resonant cavity, we try to set up a standing wave of the microwaves, right? And so this is one very common design. And what we have then is the magnetic field, here shown by the blue lines, and then perpendicular to that, of course, we have the electric component of the electromagnetic wave. And then we put our sample in the part of the resonator where the magnetic lines of force are strongest. And this focuses the part of the microwaves that that's absorbed by the sample, focuses it onto the sample so that it increases the amount of interaction here, right? What we then, as we'll see a little bit later, what we then measure is actually not directly the absorption, but the effect on the resonator, right? So when the absorption occurs, we get a disturbance of this resonance, and it's that disturbance of the resonator that we actually measure. Okay, so this is a picture of a commonly used resonator, right? And so we have a waveguide here at the back, which brings the microwaves down to the resonator. So in the microwave region, this is the typical way that we would transport the radiation. So it's at a wavelength or frequency which is too high to be passed through a cable easily. Can be done, but it's a bit difficult, right? But the dispersion of the light, if we just had our source and our sample over here with a microwave source, the dispersion of the light is way too big. So unlike a light beam, we can't direct it in a particular direction. And so the way that we get around that is to use these waveguides, right? And so this is a resonator, so basically just a box, and then there's a holder at the top and bottom that you can put your sample, will hold the sample in place and put it into the middle. In the back of the resonator where the waveguide interfaces with it, there's an opening, right? So there's a small hole here, so an entrance slit, and then above it there's a screw which can be moved up and down, which has a little metal plate on the bottom of it, right? And so what we can do with this is change the shape of the opening, and that has an effect on what the standing wave inside the resonator looks like. And so a big part of EPR, the first step, is to adjust this shape so that we have the microwaves coupled properly to the resonator.
Does that hurt your sample when you're playing? Like when you're making that decision about that opening, does it affect the sample such that you have to start over again?
I see. Yeah. So the question is that if I let me just go back. If I'm adjusting this, does that have any effect on the sample, right? So the
waves will be coming in. Right?
Yeah. And so does that irradiation have any effect on the sample? So, of course, the microwaves coming in will be absorbed by the sample, but the energy involved in EPR transitions is very, very low. And so this really does not have any substantial effect on the sample, right? All right, so what we do when we start an EPR experiment is we, on the console and the electronics that control the instrument, we can put it into a mode where we sweep the microwave frequency through some narrow range, where we can see the amount of power which is being reflected back out of the resonator. And at the resonance frequency of the resonator, the power gets absorbed. Right? And depending on the shape of this opening, so where we have the screw set, the amount of power absorbed at the resonance frequency changes, right? And so if we have the one shape, we would be what we call overcoupled, and you get the resonance here is a little bit broad, and at the resonance frequency, we have a fair bit of reflected power. And if you change the shape, then you can become undercoupled when, again, there's reflected power, but the shape of the resonance is narrower. And then in between those two, there's one critical position where at the resonance frequency, all of the energy of the microwave stays in the resonator, and there's no reflected power coming back. And this is where we work in an EPR experiment. We lock the frequency, we critically couple the resonator, and then we sit at this, exactly at this frequency. We lock the frequency at this dip, right? So at this point. And the idea is that if then we have an EPR transition occur under those conditions, then we disturb the critical coupling away from this point, and we get reflected power back out of the resonator. And that reflected power that we measure is greater than what you would measure in a direct absorbance experiment, right? And so we get an amplification of the signal. Right? And so this just says what I just said. So the reflected power that we would see is stronger than what we would measure in a normal absorbance experiment. Right? And so we're not detecting the signal directly. We're not really measuring the absorbance directly, but we're measuring this reflected power out of the resonator. And that gives us an increase in the size of the signal that we can measure. Okay, so this is a picture of a typical X-band EPR spectrometer. The fact that we're using a resonator has a really important consequence for how we do the experiment. Right? So the question is, can we now sweep the frequency, sit in resonance with our resonator, and then change the frequency and find the frequencies where the sample absorbs? And so if we look at an effective resonator, it will have a range. The range of the bottom of the dip, or the width of it, will be somewhere on the order of 1 to 10 megahertz. Right? But if you remember, I said that the width of EPR spectra is something like several gigahertz. So it's not possible, if we're using a resonator, to sweep through the range of frequencies that we want to observe. Right? So that creates a problem. Right? So we can't sweep the frequency. So what we have to do is keep the frequency fixed, and then we change the magnetic field. So essentially move, and rather than changing the energy of our light that we're putting in to match the energy levels, we do things the other way around. We keep the energy of the microwave fixed, and we change the energy levels of our system till they match the microwave. Right? So what we have to do is vary the magnetic field. And so the easiest way to do that is to use an electromagnet. And so this is why EPR is generally done at about 10 gigahertz, because the magnetic field that you need is easy to produce in an electromagnet which has a gap between the faces of the magnetic poles that are, is on the order of a few centimeters or so, right? And so, so this is why an EPR spectrometer looks like this. We have a large electromagnet here, and then a table on top. The microwave components would be contained in this box, and we have our waveguide coming down to the resonator, which sits in between the poles of the magnet. Right? We can use superconducting magnets like we do in NMR, but it becomes much more difficult to change the magnetic field if you're using a superconducting magnet. Right? And so this is one reason that we tend to stick to these somewhat lower frequencies at X-band. So here's a diagram of the schematic diagram of what the spectrometer would look like. We have our microwave source here, and then the microwaves are split into two beams. We can adjust the power going into the two beams. So this is a reference, and this is the one that goes to our sample. So we have these two attenuators here that allow us to adjust how much power is in each arm. And then we have a device called a circulator, which allows the microwaves to pass in this direction down to the resonator, and then any reflected power which comes back gets directed towards our detector and doesn't go this way. Right? And so at our detector, we have a combination of our reference beam and our signal beam. unlike optical spectroscopy, in these relatively long wavelengths, it's also possible to control the phase of the wave, right? And so we have a phase shifter here to make sure that the reference arm is in phase with the reflected microwaves, right? So that they don't cancel each other out, and so on. And then we have a detector here, which is usually a diode, just takes the microwave and changes it from an oscillating electric field into a current, a DC field. And then there's a preamplifier. Down here we have our magnet, and then there's another little piece here which we need to talk about. This is the amplifier of the signal, but it's called a lock-in amplifier. And in addition to the main magnetic field, we have some small magnetic coils on the side, and we modulate the magnetic field here when we're detecting the signal, right? And we need to talk about this because this has a really big impact on how the spectra look. Yes?
I'm just wondering, you just talked about how you have to make sure that the reference arm is in phase
Yes.
with the signal arm. What purpose does the reference arm serve? Why
Okay.
can't you just detect
Yes.
the reflected power directly?
Sure. So that's a very good question. So the main purpose of the reference arm actually has to do with the detector. So we're sitting when we don't have any reflected power. There's nothing coming this way. So we would be starting essentially from zero signal, right? And then when some reflected power comes, the detector hopefully would register that, and we would see it. Most microwave detectors are not linear in the power at very low values, right? So my signal, if I'm detecting at a very, very low value of the power, the response is not linear, right? And so it would distort my signal. But if I bias it, if I add some microwaves as a background, just lift everything up to a bias level, then the response of the detector is linear, right? And then we get a spectrum where the height of the signal we can relate to the concentration and things like that. So that's the main purpose of the reference arm. Okay, so in order to improve the sensitivity of the instrument, right? So even if we use our resonator and so on and detect the signals there directly, they're still very, very noisy. We still have very weak signals. And so we change the way that we do the detection and use what's known as lock-in detection. This is also used sometimes in optical spectroscopy, but probably the most common use of it is in the EPR. Right? And so what we do is on the side of the resonator, so you can see this sort of cap here, behind that there are just a few turns of copper wire, which are just a small coil that we can use to create an additional very small magnetic field. Right? And this small magnetic field we have as oscillating at a known frequency. Right? So we make it oscillate up and down usually at 100 kilohertz. Right? So if we're trying to detect a signal, let's say our signal is this red curve, right, and there's some absorption at a certain value of the field, we have our main magnetic field, and we would move it slowly across this region and try to measure our reflected power as a function of the magnetic field. But on top of this main field, we've got a very rapidly oscillating small so-called modulation field. And so if we're sitting over here, our field would be oscillating back and forth, and so the signal that we would get would oscillate up and down. Right? So if the field goes back and forth between these two values, the signal goes up and down between these two. And then when we're over here, on the other side of the signal, we would get a bigger change. And so we can use the height of this oscillating signal as a measure of the amount of absorbance here. One thing to notice, though, is that if I'm measuring down here, when the oscillating field is high, then the signal that I see out here will also be high. Right? On the other hand, if I'm on this side of my line, when my green curve, when the magnetic field, oscillating magnetic field, when it's high, the signal is low. Right? So if you look at these two waves, they're out of phase with each other, right? So this one, when this one is low, that one is high, right? So they have different phases. So what we plot for the EPR spectrum is the height of this signal times the phase, right? And so the phase is set to be positive on this side, right? And so we would get a positive signal when we're on this edge of the line, and on that side of the signal, we get a negative line, right? And so the shape of the signal that we measure looks like the derivative of this signal, right? And what's important actually is that if I'm right at the very top of the line, then as I modulate my field, the height of the signal, of course, won't change. And so in the middle of my line, I've got 0 here actually. So it's a bit of an unusual factor that the EPR spectrum is 0 where the signal actually is strongest, right? So you could legitimately ask at this point, why on earth would you want to do this? And the reason for doing this is that we know what this frequency is, right? So we've decided, or we have set the frequency at which the field is oscillating, and so that means that we know what frequency our signal is oscillating at. And it means we can throw away any other signal coming through that's not oscillating at that frequency, right? And so effectively what we do is filter out all other contributions to the signal except ones that are oscillating at this frequency. And that gives you a huge, huge increase in the ratio of the signal to the noise. So on the order of 1,000 times larger or so, right? And so this makes the spectrometer much more sensitive when we do things this way. So the big advantage of this lock-in detection or field modulation detection is that we have this big increase in signal to noise, but it comes with some drawbacks, and it's important to be aware of those. So the first thing is that what we get, of course, is this derivative line shape and not the absorbance spectrum, which is probably what we're more interested in. The other thing, which is perhaps a bit more severe, so the derivative, of course, you could numerically integrate it and get back the signal that we want. But the more important thing is that the amplitude and the shape of the spectrum that we measure depends on the amplitude of our modulation, right? And so when you run an EPR experiment, it's really important to choose the modulation amplitude correctly, right? So here, this is an example of some spectra of a compound DPPH, which is a standard. And so I ran these in my lab and just changed the modulation amplitude, right? And so you can see that for low values of the modulation amplitude, the height of the signal depends on the setting of the modulation amplitude, right? And that actually makes it a little bit difficult to relate the height of an EPR signal to the concentration of the sample, right? Because if I change my modulation amplitude, even though my concentration is the same, my signal will change. What's even more severe is if I make my modulation amplitude bigger than the line width, right? So if I were to take my amplitude, so here I've shown it as being much smaller than the width of this line, but if I take my modulation now and make it bigger than the line, so we're oscillating back and forth between, across the whole line, then this sort of thing starts to happen, and the width of the line that you observe in the spectrum becomes bigger, right? And we actually use this to calibrate the modulation amplitude, the amplitude of the modulation field in the sample by taking a standard like this. And if you make this number big enough, then the distance in Gauss between here, or millitesla, between here and here, is determined entirely by the modulation amplitude, right? And so when measuring a spectrum, it's important that we work in this range and not somewhere here. That, of course, is a problem if I have two species in my sample, one of which has a broad line and one which has a narrow line, right? And so sometimes it's not possible to find a modulation amplitude which is appropriate for all of the components of your signal. Usually it can be done, but not always, right? Okay, so those are drawbacks, but the main advantages of doing things this way, they're really twofold. The first one, of course, is that we get this huge increase in signal to noise. And so it makes the spectrometer much more sensitive. But the other thing that happens is when I take the first derivative, the structure of the line often becomes much more prominent, right? So these two representations are exactly the same signal, right? And this is just the regular absorbance spectrum. If I take the first derivative of this line, I get this. And here, the splitting of the line, so this pattern of structure here is much, much clearer than there, right? And so in EPR spectra, we're often interested in splittings like this, which can arise from hyperfine coupling to the nuclei, and so they're emphasized in using this detection method. So that's also a sort of side advantage. All right, so this is one aspect of detecting the signals. Another thing, though, is sort of why we have this problem with the sensitivity, and it's because the energies are so low, right? And so this means that the population difference between the two spin states, right, of the electron up and down is really, really small, right? So if you take the difference in the population divided by the total for a magnetic field of typical of an X-band spectrometer and at room temperature, this value is on the order of about 10 to the minus 3, right? So if you do the same thing for an optical transition, this number is essentially 1, right? So the signal strength for any absorption experiment depends on the population difference, right? And in a hand-waving way, you can see that that's because if I have molecules here and here, and I am in resonance with this transition, then I'll cause transitions going up and going down. If the populations are equal, then of course the amount absorbed and emitted will be exactly the same, and I'll get no signal. So in any experiment, we want this difference to be as big as possible. And in EPR, that difference is really, really small. In NMR, it's even smaller, right? So this makes magnetic resonance really quite insensitive. But it also creates another issue that we have to be aware of, and that's if I start off here with some relatively small population difference, and I start causing transitions between these two levels, what I will tend to do is equalize the populations, right? So if I turn on the microwaves, eventually, if I have enough microwave power, I'll wind up with the populations equal, and then I have no signal anymore, right? So the thing that helps in this regard is that there is, of course, a natural tendency of the system to relax back to this distribution, right? So if I were to pump some microwaves in, equalize the populations, and then wait for some time, the system will relax back to this situation, this population difference. And of course, these two processes then are going on simultaneously. And so it's important that we balance the amount of microwave power that we put in to match how fast the relaxation is so that we don't saturate the signal, don't wind up equalizing the population and losing our EPR signal, right? And so there are a couple of factors at play here. So the first one is the temperature, right? So if I go to very low temperature, the Boltzmann factor will become larger. The population difference will become larger. So here I've got the signal intensity plotted as the inverse of temperature, right? And so going to the right on this plot is a decrease in temperature. So as I go down in temperature, the signal will increase, and increase linearly as 1 over t, and this is known as Curie's law, of course. But as we go to lower and lower temperature, what we observe usually is that because the relaxation then also starts to become slow, eventually we get to a point where the signal will saturate on us because the relaxation is too slow. And so that means that typically there's some kind of maximum in the temperature dependence. So there's a temperature at which we will get a maximum power, or maximum signal. The other thing that we have to worry about is the microwave power. So if we're sitting at some particular temperature and we start changing the microwave power, we also see the same kind of effect, right? So if we increase the power, we cause more EPR transitions, our signal will go up, but then eventually we start to equalize the populations, and we'll go through a maximum, and the signal will drop again. Right? So we always have to try to optimize these two parameters, the temperature and the amount of microwave power that we're introducing. Okay, so for metalloproteins, this optimum in temperature usually is at low temperature. It depends on the nature of the metal. So some proteins, particularly ones with iron in them, have to be measured at very low temperatures, so 10 Kelvin or below. Other ones, copper proteins, are easier. They can be measured at higher temperatures. But the bottom line is that almost always when you run the EPR spectrum of a metalloprotein, you're doing it on a frozen sample, right, to get around this problem, to optimize the signal. And so that means that we have to worry about the orientation dependence of the sample, because the molecules are immobilized. They're not rotating very rapidly, and they will be in different possible orientations in the magnetic field. And this has an important factor or influence on the spectrum. So the first thing we need to look at is that the G values, so the positions of the lines, depend on the orientation of a molecule. Right? So one way to study that is if I have a single crystal, then all of the molecules in my sample will have the same orientation. And so I can put the crystal into the magnetic field in different orientations. Right? And so a simple way that this can be done is just to take a rod, which we refer to as a goniometer, and then somehow attach our crystal to the bottom of it. And then by rotating the rod, we can change the orientation. So if we do an EPR experiment under those conditions, then as we change the rotation angle, so the orientation of our crystal in the magnetic field, what we'll see is that the lines in the spectrum will move. And often we will have more than one molecule in the unit cell of our crystal, right? And so for any given orientation of the rod, we've got molecules in perhaps one or two different possible orientations. So in these are just calculated, but for this example, I've chosen 2 sites in the unit cell, and so for most orientations, I see 2 lines. There are some orientations where of the crystal where the orientation of the molecules coincide, and then we would have the 2 lines would overlap, and you might only see one. Right? So if we wanted to analyze this, we would run a whole series of spectra at different orientations. Right? Then what we would do is record the G values corresponding to each line, and record those as a set of data, and then we can plot them as a function of the rotation angle. Right? So, and we need to use the square of the G value, but the point is that the effective G value depends on this angle theta through which we've rotated the crystal. Right? And so for any set of rotations that we do, we can fit our data to this equation here and obtain 3 values, this GAA, GAB, GBB. And then if we rotate about 3 independent planes in the molecule, we wind up with these 6 independent numbers, right, that describe the position of the spectrum. Then we can arrange those values as a matrix, right? So this is actually referred to usually as the G tensor. And then numerically, we can try and diagonalize it, right? So we can do a manipulation of this to put it into diagonal form. And essentially what we have to do is find a matrix U so that if we multiply this matrix on the left by U and on the right by the inverse of U, we get a diagonal form. Right? And so the 3 values here in the diagonal form are called the principal G values, and they're what's characteristic of the molecule. They're independent of the way we do the experiment. They're a fundamental property of the molecule. Right? And then this matrix U, which we have to determine, it tells us the orientation of the axes that are associated with these 3 principal values. So each of these values is associated with a direction in the molecule, and this matrix U tells us how those axes are oriented in the molecule. Right? So just to give you an example of how this can be done in a real situation, This is some work I was involved in a long time ago where we were measuring these two iron-sulfur clusters in photosystem 1. So there are these two clusters, Fa and Fb, and they can be reduced when, if you shine light on this or if you add a reductant, you can reduce these iron-sulfur clusters. And so here are a series of spectra of single crystals of photosystem 1 taken at different orientations, and you can see that the lines, the shape of the EPR spectra, change as we change the orientation. Here it's a little bit complicated because we have two iron-sulfur clusters, and then there are 6 molecules within the unit cell, and so for some orientations we have quite a number of lines that we have to sort out. Right? And so then if we plot all of those line positions, we get this somewhat onerous-looking graph, but with a little bit of effort, each of the patterns can be fitted. You can see there are portions of each of these rotation patterns which are really easy to identify, and then by fitting this region, we can see in places like this where there are lots of points, we can figure out what's what. But the bottom line is that we're able to determine the principal G values of these two iron-sulfur clusters, but also the orientation of the axes that are associated with them, right? And in this particular case, when we reduce the iron-sulfur cluster, we wind up with a pair of iron atoms which are mixed valence, so a mixture of, one of them is Fe3 or iron 2 and iron 3, and then the other pair of iron atoms are both iron 3, right? And so from some theoretical estimations, was determined that the G value, GZZ, should be perpendicular to the axes. So these two pairs, their axes joining them should be perpendicular to each other, right? And so the Z-axis should be perpendicular to the two axes joining them, and the Y-axis should be the equal valence pair, and the X-axis the mixed valence pair. And so from this pattern, we were able to determine which of the iron atoms in the cluster was the equal valence and which was the mixed valence pair. Okay, so that's the kind of thing you can do if you have crystals. Typically, we don't, right? But before I get into talking about what we do when we don't have crystals, there's some terminology we need to introduce. So the quantities that we measure in EPR are tensors, right? So we have these 3 principal values that we can get out, and the relationships between them reflect the symmetry of the metal center that we're looking at, right? And so if all 3 values in a tensor are equal, we talk about an isotropic tensor. If one of them is different and 2 are equal, then it's axial, and if all 3 are different, we call it rhombic, right? And so an isotropic tensor occurs when you have tetrahedral or higher symmetry. It'll be axial if you've got a 3-fold rotation axis or higher. And then rhombic, the highest symmetry you can have is a 2-fold rotation. Okay, so if I take a sample, single crystals are nice, but they're rarely available. And so if I have a solution of my protein or some kind of powder of a solid, then what I get is a random distribution of orientations, and so I get a sum of all of the possible orientations in the sample. And that produces a series of characteristic line shapes depending on what the symmetry of our G tensor is, right? So if all 3 of our G values are the same, then what I will see is just a single line, right? And this will be an isotropic case, and the zero crossing here is the isotropic G value. If it's axial, I get a pattern which looks either like this, where we have a peak on one end and then a positive, negative feature at the other end, or those two can be reversed depending on whether the 2 values which are equal are larger than the one that's different or smaller, right? So we have these 2 possible axial spectra, and then when all 3 are different, we get spectra that looks like this, which are rhombic. Okay, so if we want to interpret the G values, you can use perturbation theory, and basically, this is an approximation, but basically the G values depend on the strength of the spin-orbit coupling, and so we can interpret them in terms of the spin-orbit coupling, and it's a result of the mixing of the molecular orbitals. I'm not going to get into this in any great detail, but it's possible to rationalize the values of the G values using, starting with the structure of the metal center that you're looking at, and then doing this kind of sum. Right? All right, so there's some general trends, though, that you should be aware of if you're looking at EPR spectra. So radicals which have light elements, the spin-orbit coupling depends on the mass of the elements involved, increases as the mass of the elements go up. So if I have a radical where I have very light atoms like carbon, hydrogen, and nitrogen, the G values are very close to the free electron value. So we get very small perturbation away from the G value. And the G anisotropy is also typically very small. On the other hand, if I have a transition metal, depending on how far down in the periodic table is, the spin-orbit coupling can be moderate or sometimes quite strong, and so we typically get much larger G anisotropy. Right? And this depends on things like symmetry and which electron configuration our metal has and so on. So just to give you a couple of examples of this, here's an organic radical. This is also from photosystem 1, is a chlorophyll radical cation. And if we measure our spectrum at X band, it looks isotropic. Right? And only if we go up to extremely high frequency and these specialized high field instruments can we actually see that the G tensor here is actually rhombic, right? And can measure these differences. If we, on the other hand, if we look at an iron-sulfur cluster, right, because it has a transition metal and larger spin-orbit coupling, the components here, this again is our iron-sulfur clusters from photosystem 1. We can see here our cluster FA with its 3 main components, and it's easily resolved already at X band, and we don't have to go to higher frequencies. So there's this qualitative difference between metals and organic radicals. Usually organic radicals are not resolved at X band. Metals very often are. Okay, the other component of the EPR spectra, other interaction which is really important, is with the nuclear spins. Right? So if I have, say, a nitrogen nearby an unpaired electron, the nitrogen has a nuclear spin of 1, and the energy of the electron spin states will depend on the orientation of this spin 1. Right? And so there are, for spin equals 1, there are 3 possible orientations. And so my energy level, spin up for the electron or spin down, each of those levels gets split into 3, right, through the interaction between these 2 species. And so in my EPR spectrum, then I have 3 possible transitions which at different frequencies. Right? And so I get a splitting here, and I can measure the spacing between these 2 lines as the hyperfine coupling. And it tells me information about where the electron is located, if it's delocalized, so how much time does it spend on any given atom. Right? So for a spin 1/2, I would get 2 lines. For a nitrogen with spin 1, I would get 3, and so on. So I get, for any nucleus, I get 2i plus 1 lines in my EPR spectrum through the coupling to the nucleus. Right? So typically, of course, if I'm looking at a metal center, it's going to be surrounded by some number of ligands and then perhaps protons in the protein and so on. And so if I have a group of equivalent nuclei, I get 2 times n times I plus 1 lines for the group of equivalent nuclei. And then if I have several groups, the number of lines is the product of 2ni plus 1 for each group of equivalent nuclei. And so even with a relatively small number of nuclei, this number of lines can become huge, can become really, really large. And the result is that we usually, or very often, there are so many lines that you can't really resolve them properly. Right? And so we typically only see the splitting from the strongest hyperfine couplings when we're looking at a metal center. So there are actually 2 contributions to this interaction. One is called the Fermi contact. Don't worry too much about the details of this. The thing that's important here is that it scales with the probability of finding the unpaired electron at the nucleus that it's coupled to. Right? So if there's a high probability of the electron being at the nucleus, this coupling will be large. And then there's a dipole-dipole coupling. Again, the thing to notice here is that it depends on the orientation of the molecule relative to the magnetic field, right? The other thing to see here is that this term can become negative, right? So if I were to choose theta equals to 90 degrees, this term would be 0, and I would get a -1 in my numerator, right? So the sign of this term can change. So typically we'll have some orientations where these two add, and other orientations where they cancel each other, right? And so the size of the hyperfine coupling will change with orientation. So, yeah, so anyway, if we're looking at a metal, we'll often see only the strongest coupling, and then we expect it to vary with orientation depending on the sign of this term here. Right? So just to give you some examples of how that works. So this is a spectrum of a copper center in azurine. It's been studied to death. But anyway, copper has a spin 3/2 nucleus. And so that would give 4 lines through the hyperfine coupling. In copper spectra, typically we see 4 lines which are either partially or completely resolved for one of the components of the G tensor. For the other ones, the dipolar and Fermi contact parts of the hyperfine coupling cancel each other out, so it's small. So for this part of the spectrum, we don't see that, but we can measure the splitting very easily for this one direction. Right? We can also see coupling to ligands. Right? So here's an example of a nickel center, and with a histidine bound axially to it, we get a rhombic G tensor, and but on the direction corresponding to this axial direction, we can clearly see the splitting of that into 3 peaks through the coupling to this ligand nitrogen. And again, on the other 2 components, that coupling is small because the 2 components tend to cancel each other. All right, so those are the sorts of things that we would see if we have a spin 1/2. And the question is, what happens when our spin gets bigger than 1/2? Right? So if we have more than 1 unpaired electron in our molecule. So when that happens, we have an additional interaction which is known as the zero field splitting. And this is a result primarily of spin-orbit coupling, but depending on the situation, there's also a contribution from the dipole-dipole interaction between the electrons. The bottom line is that in the absence of a magnetic field, if I look at the energy levels of the spin, they're not all degenerate. Right? So if I have a spin 1, for example, I will get 3 levels corresponding to ms equals 0, -1, and +1, and they're at different energies. And for a spin 3/2, for example, the ±1/2 levels will be degenerate, and the ±3/2 levels will be degenerate, but they will be split from one another by this zero field splitting. And this has a huge impact on EPR spectra. So when you're looking at spectra, there's a really fundamental difference between systems with spin equals 1/2 versus ones where it's not 1/2, when it's greater than 1/2. So this interaction, we describe it if we do the quantum mechanics. You can add a term to our Hamiltonian and so on. I don't really want to go into that in much detail. The bottom line is, like the G values, we also have a matrix, a tensor, which describes this zero field splitting. And there are 3 values. What's different here than with the G values is that the sum of these 3 values has to be equal to 0 by definition, right? And so what that means is if we have 3 numbers here, it's redundant, right? So if we know that the sum of the 3 numbers has to be 0, I don't actually need 3 numbers. I can eliminate one of them. And so the zero field splitting is described in terms of 2 parameters, which are labeled D and E, right? And so, and you can see we can write these 3 values in this way. Okay, and so this depends on the symmetry of the molecule, these values, right? So if I have an isotropic system, both D and E will be equal to 0. So even if I have a spin greater than 1, if the environment is completely isotropic, I won't see the zero field splitting, right? On the other hand, if it's axial, this means that D is greater or not equal to 0, but E is equal to 0. Right? And then for a rhombic system, both of them are not equal to 0. And so this ratio of E over D is a measure of what we would call the rhombicity of the system. So how far away from axial are we? If we, if you take a molecule, you can imagine changing the symmetry from axial to rhombic and so on. And so the ratio E over D is a measure of that. If we look at an organic molecule in its triplet state, the values of D and E are usually smaller than the interaction with the magnetic field, and so we get an energy diagram like this, in which the main interaction is the interaction with the field, so we have a splitting between our ms equals 0 and -1 and +1, but the energy gap here and here are different, right, as a result of this zero field splitting, and so our spectrum has two lines at different magnetic fields, right? So we have a transition here and here. And so if we measure this in a spectrum like this in a powder, now we get a characteristic pattern, which is known as a Pake pattern, and measured in EPR for a system which is rhombic, where D and E or where E is not 0, then you get this characteristic spectrum, which would have this shape. Right? So for organic triplet states, these are excited states, and so we have to use time-resolved EPR to look at that. If you're interested in this is what we do in practical EPR 3, but just to give you a sort of quick and dirty overview of how one way to do this is we set up our spectrometer with our continuous microwave irradiation. We apply a laser pulse at a fixed magnetic field, and then we can see the signal. And we also throw away this field modulation because it slows down the detection, right? And so we can measure these time traces at a fixed value of the magnetic field. And then if we step the magnetic, so measure a trace at one field, store it, move to the next field, and store it, you can generate a data set of time traces that would look like this. And then if I go back and look at in the data set at some particular time, I can extract a spectrum of the triplet state. Right? And so this is the spectrum of a porphyrin molecule here. What's interesting about this method is that the generation of the triplet selectively populates these levels. And there's really two general ways that this can occur. We can wind up with excess population in T0 or excess population in T plus and T minus 1, and this depends on the pathway by which the triplet state is produced, right? And so in the practical, what we're doing is sort of demonstrating that by looking at chlorophyll just in solution, and then the chlorophyll in photosystem 1. And there are two possible ways you can create a triplet state. One would be by just the molecule relaxing from its excited singlet state, or you could create a radical pair and have it recombine to the triplet. And these two pathways produce different population patterns, and so the shape of the spectrum, even though the positions of all the features are the same, the shape of the spectrum is really quite different, right? And so here's an example of the donor actually in photosystem 2, and you can see that it matches with this radical pair recombination, and so we know that the triplet state that we're observing there was formed by an electron transfer and then recombination. Okay, so, but anyway, the systems with spin greater than 1, excited triplet states like this is a bit of a niche area and so on, and I think for most people in this room, metals in proteins that are in high spin states are really the more important class, right? And so if we look at a transition metal now, so for example, say we have an ion with a spin 3/2, then at 0 magnetic field, we get a splitting of the levels into the plus minus 3/2 levels and plus minus 1/2. And this separation can be on the order of several wave numbers, whereas the interaction with the magnetic field in an X-band spectrometer is on the order of 0.3 wave numbers. right? So it means that the zero field splitting here, this energy gap, is much bigger than the interaction with the magnetic field, right? And so if we increase the magnetic field, these two levels, the plus minus a half levels, will split, and there will be some magnetic field value where we have a match of this energy gap with our microwave radiation. And then, on the other hand, the 3/2 levels will also split, but the slope of this line is larger than here because the value of ms is larger, right? And so there will also be another field position where this transition potentially can occur, right? And so you can see that the field for this and this will be really quite well separated from one another. And so in systems like this, the EPR spectra become very much broader than what you would see with the spin 1/2. So if we're going to analyze a spectrum like this, we would like to be able to predict where these transitions could occur, right? And it turns out that the positions where they occur really depends, if the zero field splitting is large enough, then it only depends on the ratio of D and E. So not on the actual values of D and E, but just their ratio, right? And so it becomes possible to plot a graph of the possible positions as a function of D and E, right? And so a plot like this is referred to as a rhombogram. And so this is the rhombogram for spin 3/2. And so we can plot the position of the lines here as a function of E over D, right? So as I change the rhombicity of the system, the positions of the lines will change. We should see features in our spectra which depend on, or correspond actually to, the different axes parallel to the field. So each of these lines corresponds to either one of x, y, or z. And then on the y-axis, we plot what we call an effective G value, right? So the positions of the lines in the spectrum, we can convert into a G value, even though here we're not actually talking about the real G values of the system, right? So with our spin 1/2, we saw you can, from the positions of the lines, you can get the G values. In a high spin system, the positions of the lines don't correspond directly to a real G factor for the molecule, but nonetheless we can express the position of the line as an effective G value, right? And the reason that we do this is that this graph then doesn't depend on what choice for our microwave frequency we use, right? So if I measure a spectrum using a Q-band spectrometer or an X-band spectrometer, I can use the same graph to figure out where the lines should be, right? Because the effective G value factors out essentially the microwave frequency, right? And so this is why we choose this. This can be a little bit confusing though as a novice, because you read G value and then you think this should be something to do with the G tensor, right? But in fact these are effective G values. In any case, what we can do there is learn something about the symmetry of the environment of the ion by looking where the lines occur, right? So as an example of this is an iron-sulfur cluster that was measured here in John Goldbeck's lab in a heliobacterium. And this is the spectrum they recorded. You can see we're at very low temperature here. They measured it at a series of temperatures, which I'll come back to in a second. But you can identify approximately, anyway, a couple of peaks in the spectrum. There's something clearly out here at an effective G value of 2. And then down at very low field, we have some transitions at higher G values. And looking at this, they estimated that this edge is at about 5.4, and there's a bit of a peak here at about 4.4. Right? And so then we can go away to the rhombogram and see if we can rationalize this. And so if they suspected that because of the positions of these peaks down here, that this should be a spin 3/2 cluster. And so if you take the rhombogram for spin 3/2 and just move across the D over E range here and look for a case where you would see features at 2 and 5.4 and 4.4. The best match occurs where this sort of pink-colored bar is, right? And so the spectrum can then be explained as a spin 3/2 with an E over D value of about 0.2, right? And so we see that the rhombicity is sort of in the middle between axial and fully rhombic, right, for this case. The other thing, though, that's important for these types of spectra is the relative energies of the +- 3/2 and +- 1/2 levels, right? And this depends on the sign of the splitting. So if the sign is positive, then the 3/2 levels will be higher, and if the sign is the other way around, then one will be lower. And so you can work this out in some cases by changing the temperature. So what we notice here is, if we go back now and look at these temperatures plots, you can see that the 4.4 feature becomes weaker as we go down in temperature, but the 5.4 feature becomes higher, right? And so from that, since the 5.4 feature comes from the +- 3/2 transitions, we can see that the +- 3/2 must be lower in energy, right? Because as we go down in energy, the signals coming from this manifold become stronger, and the ones coming from this become weaker. Okay, another commonly observed system is iron, right? And so here's an example of this. This is a high-spin iron 3 in a heme protein. Typically what we see is a very strong line at an effective G value of about 6, and then a weaker signal around G equals 2. Right? And so if we again go away to our rhombogram, iron 3 should be spin 5/2. And if we look at E over D equals 0, our heme has a very, quite symmetric environment, has roughly 4-fold symmetry. And you can see this matches really well. We have in the MS equals + - 1/2 manifold, we have 2 transitions at G equals 6, and the 3/2 will also have a transition at G equals 6, and then there's 1 transition at G equals 2 if E over D is 0. Right? And so we can rationalize this spectrum quite well in terms of the very essentially axially symmetric spin 5/2 system. Another thing that happens, though, with iron and iron proteins is that we often have what's known as junk iron, right? So if I have an iron protein and I'm trying to isolate it and purify it, very often there is iron present in my preparation, and there will be sites on the outside of the protein, perhaps, which can act as weak ligands to the iron and so on. And so it's often very, very difficult to remove all of the iron from the sample and only have the site that you're interested in. So here's an example of this is a study on a quinone oxidoreductase, or NADH quinone oxidoreductase. And the authors were really interested in this flavin radical. But what you see in their spectrum is that they have this peak at 4.3, as an effective G value of 4.3. And if we look at our iron 3 rhombogram and we go to the maximum rhombicity, you can see that in this part of the rhombogram, 3 transitions converge at 4.3, right? And so this is really characteristic of iron in a very asymmetric environment, right? And so if we have an iron atom which is binding in some sort of not really well-defined binding site, then its environment then is usually quite asymmetric. And so there's this peak at 4.3, which arises from this iron, which is usually not very interesting in terms of the function of the protein. This is just some what we call junk iron, which couldn't be removed from the protein completely, right? And so this is also something to watch for if you're measuring an iron protein spectrum and you have this line at 4.3, it's probably not something that's really interesting, but rather just an artifact of the preparation that removing all of the iron was difficult. Okay, so, yep.
So I've heard that argument before.
Yeah.
And in my mind, like if you put a ferric ion inside a protein environment,
Mm-hmm.
it's bound to be pretty asymmetric already, right? And then if it's somehow in water,
Right.
it's potentially more symmetric.
More symmetric, sure.
Do we know, the junk iron or the other term that's used for it, do we know anything about what that actually is on a molecular structure basis?
Not to my knowledge, really. So it's often actually difficult, I think, if you're studying a system where you have a somewhat asymmetric environment to start with, which is the one you're interested in, to decide if all of the spectrum you're looking at is really coming from the iron that you're interested in, and how much of this is something that's somewhere else in a different environment, right? So, and that can be a real problem. If you've got a very symmetric environment, like in a heme protein, then you're in good shape because you can easily recognize the junk iron from the heme iron. But in other circumstances, it can be tricky to distinguish those. Okay. Anyway, that's where I'm going to wrap up. Hopefully, I've been able to give you some kind of a better understanding, perhaps, of the basics of how EPR is done, and have been able to show you how we can determine the orientation dependence of the G values, and that this is really important for studying systems in the solid phase or where they're frozen and so on, and that sometimes we can get hyperfine couplings, and gave you a little flavor of how we deal with zero field interactions. There are two other talks here on EPR, so by Stefan Stoll in the coming days. He'll go into more detail of characteristic EPR spectra and how you can recognize different properties and so on. And then there's a talk on more advanced methods using pulsed EPR, which is useful for getting out, for example, small hyperfine couplings, which we can't see directly in the EPR spectrum. Anyway, with that, I'd like to thank you for listening so attentively, and I'll take any questions you have.
Okay, thank you, Art, for the really nice, lucid lecture.
Thank you.
Art and I coordinated this lecture with EPR1. So those of you who are taking EPR1, you'll be looking at a slow relaxing organic radical. You'll be looking at a fast relaxing iron sulfur cluster. You'll be doing temperature dependencies, power dependencies, amplitude modulation dependencies, and we'll finish up with a high-spin system. So if you're doing that, much of this will be reinforced on real time in the laboratory. Are there any questions for Art? Marty?
Since you were looking so beautifully and clearly at the hardware, I'm wondering, is there a fundamentally different way to detect an EPR transition that would perhaps, just be a game changer? I remember maybe 20 years ago now, a group at Emory was trying to use a squid susceptometer to detect EPR transitions. Is there anything else on the horizon that might come one time to replace?
I wouldn't, completely discount that, but I'm certainly not aware of any real, potential game changer. I mean, the big development, of course, this is now getting on sort of 25 years ago and so on, but was the introduction of pulse techniques, and you can measure the EPR spectrum using spin echoes to detect it, and in some cases that can have distinct advantages over using field modulation detection, but this still remains the main way that it's done, and I don't think we're likely to see that change in the near future.
Any further questions?
I might have missed something about how do you assign the magnetic axis to the molecular directions for a single crystal? EPR?
Yeah, so that comes out of, I showed you this transformation of the matrix, right? So if we can measure our rotation axes, right, our rotation patterns, and we then have to do this diagonalization. And in doing that, we do that numerically, right? There are numerical methods which will allow you to determine this matrix U, right? Maybe if I should go back to that.
But don't you need at least a rough idea of the molecular orientation of the crystal within the spectrometer?
Yes. Let me just see if I can find that here. A couple more here. So in the experiment, we measure these values, of course, and then numerically we try to determine this matrix U. And the elements of this matrix are the direction cosines between the principal axes of the G value and the axes about which we rotated. Okay? And so initially what it will give you is the relationship between the axes of the crystal, right? So if I have crystallographic axes A, B, and C, then I can find the angles between A, B, and C and the axes of my G tensor. If I have an X-ray structure, I should probably have emphasized this. If I know the orientation of my molecule in the crystal, then of course I can transform my G value axes, or G axes, to the molecule. And then I will know what direction in the molecule each G value belongs to. If I don't have that information, if I don't have the X-ray structure available, then all I get is the relationship between these G axes and the macroscopic crystal axes. Right?
Yeah. Okay, we're getting off on time a little bit. Art will be here all week, and so he'll be available for answering questions. So if you join me in thanking Art once again.